Okay, welcome to the second in our new screencast series. Our plan is to discuss increasingly complex examples built with MPS. In the previous screencast, we have talked about the unless statement, which is kind of the hello world of language extension. And now we're going to talk about decision tables. And the person you're currently hearing talking is Markus Voelter, and I'm together with
Vaclav Pech.
Here at the JetBrains living room in Prague.
It's actually a conference room, but
it has a fireplace.
Yeah, that's right.
Okay, so what we're planning to show you is how to implement the decision table. And the decision table is basically a tabular notation for nested if statements.
Exactly. So it clearly shows the benefits of being able to use projectional editor. Because you're no longer restricted with ifs and indented layout. You can create a table that acts as piece of code.
Right, and this is actually a very nice example because by looking at that, literally, if you guys who just now watched this video, if you look at this code, you probably intuitively know what it means, right? It basically ANDs the condition in the row header with a condition in the column header. And it's implemented as a nested if statement. So if is male and is baby, or if is female and is adult, then these are the respective return values.
Right, and the values in the table doesn't have to be constant values. They can be expressions, right? So anything that, so you can like add them 10 plus something.
Yeah, now we're actually dealing with the Czech keyboard, which means that Markus has problems. But this can be complete, as you said, expressions.
Expressions, yeah, as long as it returns, in our case, an integer, then it can be a value in the table.
Right. So as Vaclav just said, it has to return something because it is an expression. So it can be used as an expression. You can actually, literally, you should be able to multiply the whole table by 5, which means that whatever it evaluates to, the result is multiplied by 5. So it can be embedded anywhere where Java expects an expression. Like, for example, here we have it in assignment statement, but we could also, if we had a method somewhere, like I'm adding a method here, dummy, which takes an int x, I should be able to call dummy here, and then putting in a decision table, so I have a method call with a whole decision table in there.
As a parameter.
As a parameter, because it just is an expression. So that is possible. It's not necessarily maybe a good use case, but it's possible. So I guess we should explain how this stuff works.
And I think the best place to start would be the structure.
Right.
So let's look how the structure for such a table looks like.
Yeah, okay. So you can always use Control-Shift-S to go to the definition of something, to the concept declaration. And here you see the concept declaration of the decision table expression. And you can see that it is an expression because it extends from Java's expression concept.
So anywhere where you use expression, decision table would be a good fit.
Right. And by the way, we're not going to say anymore that our decision table language extends base language. You should kind of understand that. And if you don't, go back to our first video, the unless statement, where we mentioned these things.
Right.
Okay, so then the structure of the decision table is straightforward. It contains a collection of expressions for the column headers, a collection of expressions for the row headers, and it contains a bunch of other things, which is the content cells. Like
if let's call them that.
That is true and that is true, then we return this. We have to do some arithmetics to find the right cell. And then we also have an expected type, like whatever we return from the table, it must be int or whatever. And we have a default value for the case that none of the conditions hold.
Yeah. So if none of the conditions are met, then the default value is returned instead.
Because it has to have a value, so we can't just do nothing.
Right.
Okay.
And again, we have an alias, I see.
Right.
So that you can type it in and get code completion for it.
Yeah. I mean, since it is used in a basically text editor, you have to have a way of instantiating a decision table. You can't just start drawing lines. And we do that by using the deck tab abbreviation here.
Well, now I think, how would an editor for such a concept look like?
So let's
How
go
difficult would it be to create one, actually?
Actually, this one is really
Hey.
trivial.
It is.
Yes, because the magic happens in a pre-existing base class. So the editor for decision table is basically a horizontal list of cells. In the first cell, it expects, or it puts the expected type, like int. Then there is the keyword, the constant default, and then the default value itself, which is, as we said, an expression. And then here, that's the table.
That's a table. Oh,
and
the
so
whole table.
You just enter a node of type table. To get this to work, you have to go to the editor's properties and include the JetBrains MPS lang.editor table. So the table's support is in a separate language. So that needs to be done. And you should, in the imported models, you should include MPS lang editor table.runtime, because that already contains a couple of useful utility classes for working with tables.
I see. Okay.
We're going to use one. So basically the way tables work is you simply put in a table node thingy here, and then you have to implement a table model. This is just like in Swing, where you have to implement a table model.
Right. Basically, you have a view and a model, and the model is what you have to define here.
And the good thing is that there is already a pre-existing class, a table model implementation, that deals with the kind of logic we need in this case. And this is called the XYZ, stands for XY contents table model. And basically you pass it the node you want to represent. In this case, it's our decision table. And then you basically use reflection to pass in the three collections which contain the column headers, the row headers, and the content cells. And you use the link construct. So basically this says it's the col headers link of the decision table. So if you jump here, it's that guy, right? We've seen that before.
Right. Yeah, well, this is the structure of our table.
Yes.
Right.
And going back here, and the last argument is the editor context.
Right. All right. And the model is clever enough to sort it out, to map the column and headers and the actual cells result values.
Sure. I mean, you can actually take a look, right? This is the implementation of that guy. It basically does the usual. I mean, it does what you would expect, right? It has to do this kind of logic to find to map a two-dimensional array of content cells to a linear list.
Right.
I mean, that's just how you would do it. I mean, I'm not going to say anything here, and yeah, that's all.
All right.
So that's the trick. Well, this gives us this editor, and you can insert new columns, new rows by pressing enter at the correct places. So, well, that's the editor.
Cool. Very cool. Now, so we have the structure, we have the editor. Do we need something else?
Yeah, we need type system rules.
Right.
Because if we say that guy is the expected return type, then we want to make sure that these guys actually are.
And all right, so what if I type a string in here? What happens? Let's say 50. All right. Well, it seems to complain about string is not an int.
That's true.
Does it work for the default as well? We have to be really careful because even the default value. You're right. Same thing. Good.
Okay.
So even the default is protected by the type system.
Yep. So let's see how that works. Let's go to the decision table. Type of decision table. Here are the type system rules.
Hey, that's not much. That's less than a page of rules.
Yeah, it's a little bit more than in the unless example, where we just restricted one single expression. Here we do a bit more. So let's step through the various lines. The first thing we do is we say that the type of the whole decision table, remember it's an expression, so it has to have a type.
Right.
So the type of the whole guy is whatever is in its expected type field copied. We have to make a copy because otherwise the same type object would be kind of placed in the type system tree internally into two places, which is not possible because what tree has always been contained by one parent. So, I mean, it's the usual primary containment structure stuff, so we just have to create a copy. That's easy.
Okay, I have to remember that then.
Right. So then we step through all the row headers and establish that thing. That is actually interesting because we now say that the type of each of the expressions in the row header collection has to be Boolean or a subtype of Boolean.
Yeah, conditions must be Boolean.
Exactly.
Of course.
Yeah.
Now, one thing I noticed at the first line, the type rules seem to be slightly different. You know, one of them seemed like be inferring the type, and the others seem to be checking for type. Is there some?
Yes.
So there's probably something that must be mentioned.
Yeah. So the MPS type system engine works by a unification, which is a nice algorithm you can read about in various books and wiki pages. But the point is that it can do inference of types and type checking with the same formalism, which is very nice. However, in this case, we really just want to make sure that the type is checked. There doesn't need to be any inference. Here, we need inference because we want to say that we want this type to be derived,
so we need
inferred
right.
as that guy. This is why check only is false. Here...
And that's the default, isn't it?
Yes, that's the default. And here check only is true, which means that it's only a type check and not an inference rule.
Mm-hmm. Mm-hmm.
Right.
Good.
Then we do the same for the column headers.
Yeah. Clear.
Same problem, same story.
And then the actual values.
Yeah, and now they don't have to be Boolean, they have to be subtypes or the same type as the decision table itself, which we just established here.
Mm-hmm. So we just checking that the values are compatible with the type that we set on the whole table.
Right. And we do the same for the default value.
Default value. Mm-hmm.
That's all.
Cool.
That's
pretty intuitive.
Absolutely, yeah. Once you get used to thinking in terms of unification and type inference, it's actually pretty neat.
Mm-hmm.
It's actually one of the really cool aspects of MPS, this engine. Okay, so that is all about the type system. There isn't anything else to say.
Awesome.
Cool.
So we're probably missing just one little piece, and that's how to generate this into Java. Right?
Yeah. And that is actually not trivial.
Mm-hmm.
The reason is this. If you go back to the sample here, well, okay, one step back. We already said that this decision table is basically a better representation for nested if-else statement. And if, as I just said, is a statement. So we have to use a bunch of statements in an expression context, right? An if statement is not an if expression, so you cannot just use it in an expression. So we have to find a way of creating an expression here instead of the table, which itself can contain a bunch of statements. And since Java itself doesn't have closures, there are basically two ways. You can either use inner classes, or Java may have closures soon, and BaseLanguage does have closures, but we implemented it as a method. So what we are doing is, for each decision table, we are creating a helper method in the surrounding class, which contains all these if statements, and then we replace the decision table itself by a call to that method.
Right. I see. Call to a method is an expression,
right?
So it can be in place replacement for the table. Yeah. And inside that method, we can do the if statements as we like. We can nest them.
So let's look at the generate code to better understand this.
All right.
So it's just a preview generated text. We go to the decision
here
sample, and here is the thing, right? It has a stupid name, which is unique and nothing else, and it basically contains these nested if-else statements.
Right.
Now what you'll see here is that this method has arguments, because we have to transfer the context here, which in this case is the person guy, right? We have to make that variable available in that method.
In the method, right.
So that makes it non-trivial.
Because inside the newly created method, you need to access all the elements from the context where the decision table is being used. So we have to pass it to that method.
Yes.
Right. Yeah, I see.
So let's look at how it's done. So we have mapping configuration, which determines what happens. And there are two rules. There is a weaving rule, and there is a reduction rule. Reduction rules, as we've seen in the unless example, replace the occurrence of a decision table with something else. A weaving rule is a bit different, because when it finds an occurrence of decision table, it also creates something else, but it doesn't replace the decision table with it, but puts it somewhere else.
All right. So it creates new stuff in the target.
Right. So let's look at the new stuff it generates. Look at this template decision table, and you can see it creates this new method. It's wrapped in a dummy class.
Right. Yeah. So it actually is a method, right? I can see public, then int, the name of the method, and arguments.
And stuff.
Yeah.
And we will get back to that in a second. So we just look at the big picture first. And so the question is, where does this method go? Sorry, I closed the wrong thing here. Where does this method go? Well, a weaving rule also specifies the place where the new thing it creates should go to. Remember, it doesn't replace the decision table. It should go somewhere else.
Yeah.
So what we do here is we take the generation context, it's passed in here, and we get the copied output for an input. So the thing is, a transformation always maps an input model to an output model, and we want to put the method we generate here not into the surrounding class in the input model, because the input model is just what we've just been editing. It should go into the output model, into the class that corresponds to the class that contains the decision table in the output model.
Right.
So we grab the output model and use this get copied output for helper statement, and from our decision table we go up to the parent hierarchy until we find a class, and we then get its representation in the target model. And that's where this stuff is put.
All right.
Good. Okay. So, the type of we can now discuss this method, right? So the type of that method obviously has to be the expected type of
the method has to return the same type that the decision table does.
Exactly.
Yeah.
The name of the method should just be unique. And we have created a helper method on the decision table concept, which just uses some way of trying to get something that's unique. Doesn't matter.
Right.
Not going to talk about it. The next thing we should look at is the arguments, because that's really the interesting part.
Right. I see two arguments, right? There's local variables and parameters.
Yeah. So let's think about it first. We need to pass in all or references to all local variables which are used from within the decision table.
Yeah, obviously. That's like the person reference to the person variable that we were referring to from our table.
Right. And the same is true for all the parameters of the method that contains a decision table.
Right.
So we have created a helper method referenced LVD's local variable declarations that is also defined on the decision table. So we can go here. So this is the behavior for the decision table. And this method referenced LVDs just simply grabs the decision table object, grabs all its children, filters them for instances of local variable declaration.
Oh, references. Local variable references.
Yes, it looks for all the local variable references and gets their referenced declarations.
Oh, right. And here we're using the collection language, don't we?
Yes, we use the collection language. And, we put it into a set so we avoid duplicates. So if we have several references to the same variable, we only get one entry here.
Right.
And then, by the way, we do exactly the same for the reference parameters.
So we look at all places. So let me try to explain this so I better understand it. So basically we go through, so we look at the decision table, and wherever inside the decision table we refer to some parameter of the method that the decision table is in. So we take those and we turn them into the original declarations of the parameter.
We don't turn them into, we get the original declaration from
So we retrieve the declaration of the parameters that we're referring to. And since we are storing in a set, the params thing is a set, so we don't get duplicates. So we get only the definition of parameters that we use inside the decision table.
Yeah.
Okay, clear.
Yeah, okay. And then, then we loop over these collections, and then we create a new argument whose type is the type of the variable declaration we're iterating over, and whose name is also the same.
Right, okay.
And we do that for local variable references and for parameter references.
And they are all passed as arguments to the newly created method.
Well, yeah, technically speaking, we're creating the formal arguments here. The passing of them has to be done somewhere else.
Right, So we created the method.
Yes.
But we're still not calling them.
Right. So let's, for the time being, ignore the inside of the method and go back to the place where we actually supply the values for these arguments. So going back to the mapping configuration, we already talked about the fact that we also have a reduction rule, which takes a decision table and reduces it into, well, a method call. Here is a method call, a dummy method call to a dummy method, right? And, well, basically we rewire the reference to this dummy method to the method that has the name we just uniquely defined through this behavior method. So in other words, this is a reference macro, and when we run this generator, we don't inject the reference to generate deck_tab method, but instead to whatever method this name identifies. And so then we have to once again loop over those local variable declaration thingies we collect and create a new local variable reference, because we want to pass an expression that references that local variable for each of the local variables we address from within our decision table.
Right.
And we do the same for the arguments. So that sets up this whole extract a bunch of stuff into a separate method. It's a bit like a refactoring, right? If you think about it. Refactoring has to do the same stuff. If you do an extract method refactoring, you have to do the same analysis.
Oh yeah? And yeah, that's a valid observation, actually.
Yeah. So this would basically tell you how to write a introduce method refactoring. It's exactly the same problem.
Cool. Yeah, it looks like this is a very, universal idea, and well, this piece of code could be reusable in some way.
Yeah, actually, there is something like that. There are many contexts where you replace an expression with a bunch of statements, and this is also known as an expression block. It's basically an expression that contains a block of statements. And so that could be refactored into a separate language concept, and then we could use that language concept when translating the decision table.
All right.
But we didn't do that. So, okay, we're almost there. Let's look at the implementation of the method, which is actually not very sophisticated. Basically, we now have to build this nested if statement.
Yeah, out of the table, right?
From the table.
So we have to go through all headers and columns and return the appropriate value. Yeah. So we have to turn it into if statements. Okay, good.
So we have an if statement here. And if you don't understand this copy source notation with an if statement, go back to the unless tutorial, because that's exactly what we had there.
Oh, right, yeah.
So we're iterating over all the column headers. We're generating an if statement for each of them. And then in the condition, we just put the node itself, because remember, the column headers are expressions. And we want to just put this expression into the if statement.
It's the is male, is female.
Yeah.
Right. All right. So call to these methods. Yeah. Or any Boolean expressions.
Right. Yeah. And then within that if statement, we have another if statement, which now loops over all the
row headers.
I'll talk about that in a second. It loops over all the call headers. Row headers.
Row headers, right.
Call headers on the outside. We now have row headers on the inside. And we again use the same expression thing. And then we actually return a value, which is basically at the crossing between the cell, call header, row header crossing. And this is where we have to do some math, right? So we basically grab the row header and the call header. We can use the .index function, built-in function, to give you the position at which a certain node is located in its parent's collection. And then we basically do the usual math again, right? To index into them.
Right. So yeah. So we have a row header of some index, and we multiply it by how many columns there are. Yeah. And we add the index of the current call header. Right. Okay. Good. Yeah.
Right. So and then this gives us basically the result value, and that's basically it. There is the default, which is just a copy source of the default value.
Right.
Now there is one little more thing to explain.
I noticed, yeah.
There was a bit more stuff, right? So the problem is this. When we want to find here the content cell, which is at the crossing between the call header and the row header, we obviously need to know the call header cell and the row header cell.
Right.
Now, our loop macro here iterates basically over the row headers. So inside that loop macro, we have a variable node, which represents the current row header.
Row header. So we have it. So row header is fine.
That's what we say here. The row header is just the node. The problem is the call header.
Oh, has it been forgotten?
Yes.
From the outer loop, we can't see it.
Yes, there is no way of passing down the context easily. Maybe that's going to be changed at some point in MPS. But currently what we have to do is we have to, when we iterate over the row headers, in each of these row header nodes, we put the column header, which here is known as node, we put that into a user object. So MPS model nodes can contain arbitrary crap in its user nodes object. We get the adapter, that's basically Java class, and use the put user object, the hash map. Under the name call header, we put the node, which at this point refers to the node call header. So we just iterate over all of them, put it here, and that's it.
Yeah. So we save it. We save it for later. Yeah,
and then inside we can use we can get it out again. So we have our node, we get the adapter, do the get user object, we do a downcast, and that's the call header.
Perfect.
And this way we can pass down the context established at the outer loop.
Good.
That's it.
Cool. Is it all we need to have decision table work in?
Yes.
Great.
Yeah, and so just to give you an expression, because this all sounds perhaps quite complicated, but if you're familiar with MPS, this can easily be done in an hour.
Right.
So this really shows off the power quite well.
Yeah, we got pretty far, and if you know what to do, it's not so much code.
No. Yeah, that's also an interesting observation, that working with MPS is quite dense. You don't have to write much, but you may have to think a bit about what you have to write, which is a very good sign for DSLs, because it avoids unnecessary, boilerplate stuff.
Right.
Makes working with it sometimes a bit tiring. Okay, cool.
Yeah, this code again is available at GitHub, right?
Yep.
So whoever's interested in how the decision table has been implemented and wants to play with it themselves, just go and grab it. The links will be put wherever this video is.
Yeah.
So it shouldn't be difficult to get it.
Cool. So, thanks for watching.
Thanks for watching.
Ciao.
Goodbye.